Hey, all you cool cats and kittens. This is Miss Chang here, bringing to you session 3, week 420 to 426, the first week of marking period 4 for Rockville High's chemistry classes. So our topic this week is 17.1 Thermochemistry. So this is going to be part of a 2-week topic. And the next slide, we're going to introduce the key terms and equations that we're going to learn by the end of this presentation. So we're going to learn about something called heat, which is represented by the letter Q, enthalpy, which is delta H, and that's going to be used interchangeably with heat, the word thermochemistry, endothermic processes, exothermic processes, the calorie, which is CAL, joule, J, heat capacity, which is joules over degrees Celsius, specific heat, which is joules divided by grams times Celsius, and the specific heat equation, which is Q equals M times C of P times delta T. So all these equations and terms will be important next week as well. So please make sure that you know them. If you don't know, rewatch the video, or you can look at the extra resources we posted at the end of this video. Right, so going over our learning objectives, this is what we're going to learn by the end of all of our videos. So the first one is the total change of energy in any system is always equal to the total energy transferred into or out of the system. So this concept is called the conservation of energy. Second one is that energy cannot be created or destroyed, but it can be transported from one place to another in between systems. So our agenda today is that we're going to be watching session 3 YouTube videos. So there's 3 parts, so I try to break it down so it's a little easier to digest. You don't have to rewatch the whole video and try to rummage around for something. You could just watch one of the 3. When you're done with watching all your videos, you're going to be answering 17.1 Thermochemistry practice problems, which is a Google form. It's going to give you the answers immediately, and you're going to get the feedback. I want you guys to look at that feedback so you can figure out what you did right, what you did wrong. You can revise the answers if you want, but that's going to be just 10 points in your classwork category. That's completion. So don't worry about getting your answers incorrect, but we want you to know why you got the answer right or why you got it wrong. And then before Sunday, so due date Sunday of 426, we have our exit card. It's going to be 5 questions, also Google Forms, and that's going to be in the all task category, which means it's for accuracy. You're going to be able to change those answers before Sunday, but make sure that you understand why you're answering a certain way. We want to give you the freedom to understand why you're answering a certain question. So we're not going to penalize you where you only have one chance. You change it as much as you want, but after Sunday, we're going to grade what you have. All right, so to get us familiar with our scenarios for thermochemistry, we want to introduce a few real-life scenarios that you might encounter. So the first one is when you order your cup of coffee. So some of us like to hit Starbucks before going to work or going to class. The cup of coffee you order before class will start to lose heat the second it's poured into the cup. However, you probably can't drink it until like halfway into first period if they made it the right way, because it takes quite a bit of time for that coffee to cool down. I'm sure many of us have burned our tongue on a cup of coffee. I know I have. The second scenario is that whenever you order French fries, like from the McDonald's drive-thru, they tend to be cold and soggy before you get home. So this is something that I'm familiar with. I was reading a Reddit chat how French fries are the best in the car. They're very hot and they're steamy and greasy when they're in the car, and they never seem to get home. I know that I prefer my fries in the car. So we want to wonder, why do some things cool faster than others? So before we get started with the lesson, we want to familiarize ourselves with a few definitions. The first one is energy. Energy exists as 2 forms. One is work, and the second is heat. So work is not really what we want to focus on in chemistry, but that just means the ability, a force acting on an object to make it move, such as gravity, that is work. And heat is what we're going to learn about today. So energy is going to be represented by by the symbol E, and it has a unit of joules. So capital J is for joule. That's a unit of energy. This is our international science metric unit is J. That's what we use worldwide. You also might hear it used as a calorie. So that is not the SI unit. However, calories are used for food, so you've probably read about calorie counts on the back of a piece of candy or a bag of Takis you've eaten. So calories can be converted to joules and vice versa. So 1 calorie is equal to 4.18 joules. So heat. Heat is defined as the energy that transfers from one object to another due to a temperature difference. And this is represented by the symbol Q. So please note that heat is different than temperature. So temperature we've talked about earlier in the year, and this is the average kinetic energy of particles in a substance. So going back to our KMT lessons, kinetic molecular theory, that all atoms, all particles, all matter is moving even if you don't see it at the microscopic level. So it could be vibrating in place, it could be spinning around, or it could be moving, sloshing around on the XYZ axis. So temperature has the units of Celsius, Kelvin, and Fahrenheit. So this little illustration here shows you these little particles. So this could be gas particles at lower temperatures. So this one's at 20 degrees Celsius, I believe. These vectors show that it's moving a little bit because of the as less kinetic or moving energy than something that's higher temperature. So if you increase the temperature by 40 degrees, those vectors right here, which shows movement, increases because it has more kinetic energy. So thermochemistry, what is it? It's a very long word. So thermochemistry refers to the study of energy changes that occur during chemical reactions or phase changes. You could also define it as a study of enthalpy. So enthalpy refers to the heat content of a system at constant pressure. So everything has heat. As we mentioned before in the year, that everything is going to have energy and everything is going to be moving even though you can't see it. So unless we could get to absolute zero where there is absolutely no movement, everything will have enthalpy. So for our purposes, heat is going to be the equivalent to the change in enthalpy. So here's a picture just to briefly show you what's going on. We have an object A and an object B. A is at a higher temperature than object B, lower temperature here. You can see the difference in the vectors, showing that the atoms, the molecules in object A is moving a lot faster and more than object B. Whenever you push the two together, you mix them around. So think about that energy effect simulation we did during session 1. These things are going to interact together, and what's going to happen is that energy is going to flow from one to another until everything's the same temperature. All right, so let's introduce you to the zeroth law of thermodynamics, which is referring to the direction of heat flow. So this is a very important concept for you guys to know, is to know that heat always flows from a warmer object to a cooler object. So that's called the zeroth law. It's so fundamental. Didn't even give it 1, gave it 0th. It's the main idea. So in the diagrams below, we show you that object 1 and object 2 are going to be mixed together or put together, that when you have a hotter object next to a colder object, is that heat will always flow from hot to cold. So the direction of heat flow will always be from hot to cold. So thinking back to our session 1 FET, the iron block that was heated transferred heat into the water, and the iron block dropped in temperature. So whenever it dropped in temperature, you didn't see cold packets from the water being moved to the iron block. So there's no such thing as cold energy. You saw that the iron block was losing or giving away its heat energy to the water. So I like to think that cold actually is not a object by itself, that the definition of cold is the absence of heat. So for example, if you like iced coffee like I do, I like to add a lot of ice to my coffee. The ice will absorb the heat energy from the coffee, and the coffee will drop in temperature until both the ice and the coffee are at the same temperature. So in picture, the second diagram right here, it shows that object 1 and object 2 are the same temperature. So heat is always going to be transferred from hot to cold until both objects are the same temperature. When both objects are at the same temperature, we call that concept thermodynamic equilibrium. That's when the rate of heat transfer is the same between the two objects. So there's no more heat flow. All right, so this leads us into the first law of thermodynamics. So heat always travels from hot to colder things. Got it. But there's only so many things in this universe. Where does all this heat energy go? This first law of thermodynamics tells you that energy cannot be created or destroyed. So it's represented here also by this equation, that the total energy, remember that delta means total or sum of all energy in the universe, is going to be equivalent to all the energy in the system, the change in energy in the system, plus the change in energy of the surroundings. And then the difference, when you add those two up, it's always going to be 0. So remember that all matter in this universe has energy, and heat is constantly being transferred in the universe all the time from hot to cold, hot to cold, hot to cold. And technically speaking, it won't stop until everything in this universe is at thermodynamic equilibrium. So imagine life as a game of hot potato. You have the heat packet and you don't want to hold it because it's really hot. You're going to keep on tossing it to the next person. But there's only so many people that have the potato. So this is very complicated. So you can imagine you sitting at your desk right now watching it, that there is a lot of heat transfer going on. So your bum that's warm because of all the energy from the food, creating bodily heat is being transferred to the chair. However, you might have the hot laptop on your lap. It's transferring heat onto your lap. And then maybe you're transferring some heat into the air because you're sweating. There's a lot of heat transfer going on. How do you possibly study all of this? So that's where we want to define the system and the surroundings. We want to simplify this. You don't want to keep track of all the different heat transfers going on within the universe because it's infinite. It's going on all the time. So in thermodynamics, we like to simplify the equation by studying isolated parts of the universe. So first, we want to define the system. So we're going to use this picture to show you. The system is the part of the universe being studied, what you care about. So the system can be a chemical reaction. It can be an object like your body sitting in your room right now, and you want to relate it to maybe your chair. So you can also define your system as either open or closed. So an open system, matter can move freely between the system and the surroundings. So if you had a chemical reaction, say the combustion of methane with oxygen gas to produce CO2 and H2O, if the methane and the oxygen can just leave the container, that is an open system. Whereas a closed system, it's going to be sealed and the reaction is going to be contained into a certain area so that matter cannot leave. The only thing that can leave is going to be energy. For the most part, we like to study closed systems. So if the system is what's being studied, the surroundings is everything else in the immediate vicinity of the system. So this would be, in the case of this picture, this will be the air around the system. This will be the beaker, not the chemical reaction itself. And that too combined together will equal the universe. So when we look at the system as what we're studying, we could describe it as either endothermic or exothermic. So the first term we're going to go over is going to be endothermic processes. So when the system gains heat, the surroundings cooling down, we'll describe an endothermic process. So looking at this container, so this round bottom flask represents the system. That means everything else, the air around it, is the surroundings. So when the arrow goes into it, this system is gaining heat. That means that the surroundings must have lost heat or given it to the system. So this means that your system also, in another definition, is going to be absorbing heat from the surroundings. So within this box, the whole universe, there's no net change because whatever the surroundings lost to the system gains. So we assume perfect fidelity that there's no energy loss during heat transfer. So whenever you have a chemical reaction, the heat or energy is going to be written on the reactant side of a chemical equation during endothermic processes, and the system has positive Q and positive delta H values. So right here, if you see a positive heat value or a positive delta H, we call it an endothermic process. So remember before we left for quarantine that we showed you energy diagrams showing the reaction coordinate of a chemical reactions. Endothermic processes will absorb energy, and you're going to get a positive delta H so that your products will have more energy than your reactants. So in terms of a chemical reaction, we can apply it to something that you're already familiar with, photosynthesis and respiration. So for photosynthesis, carbon dioxide and H2O is taken in by trees, but the process cannot happen unless you have energy, and that energy comes from the sun because the plant is absorbing energy from the sun. If we refer to the plant as the system, that is an endothermic reaction, and allows the plants to absorb the energy and store it into the bonds of glucose, C6H12O6, and some O2 gas. Well, the opposite reaction, when you flip it around, is whenever you consume glucose and breathe in oxygen, that's going to produce CO2, H2O, and also energy. Remember, whenever you eat glucose, you eat sugar, that produces energy. So when energy is expressed on the right-hand side, we're going to call that an exothermic process. So let's go closer into exothermic reactions. So exothermic reactions, on the other hand, is whenever the system loses heat, the surroundings become warmer. So once again, this is our universe. It's all stored within this box. The flask is our system, so all the air in the container will be the surroundings. So whenever the system loses heat, so the flask releases the heat, the surroundings will absorb all of it. Once again, the net change within the box will be zero, but the system itself is losing the heat to the surroundings. And then so you could therefore assume the surroundings is absorbing heat. Because we study it from the point of view of just the system, we're going to say that the system has a negative heat value, negative Q, and a negative delta H, negative change in enthalpy. So when you write a chemical reaction, as we saw in the last slide, that the heat energy is written on the product side of the chemical equation. Going back to our energy diagrams, we have the term exothermic, and that's whenever your products have less energy than your reactants, because the reactants released energy to form the products that went into the surroundings, and your resulting delta H value whenever you have an exothermic reaction will be negative.